Okay, so right now I'm going to help you with the last section of your practice test. This is section 2.4 is what it's labeled on your practice test. It's basically the one about your dry ice, all right? So I just showed you my answer key, but this answer key is also posted on the website. It will be the day before the test so that you can check your answers, all right? So I'm just going to go through it with you on how to do it. And then you need to make sure that you try it yourself though, and then you check your answers with the answer key to see what you got wrong. Okay? Okay. So let's go through it. I'm going to read you the prompt and then we can discuss how to do it. So a student hypothesizes that the larger a block of ice, the slower the rate of sublimation. She thinks this will be the case because there is too much ice to start with, so it will run out faster. Her data is below. So maybe you read that and you're like, that doesn't sound right to me. That does not make sense. But how can we prove that it doesn't make sense? Well, we have to look at the data, right? That's the point of doing the labs, is we can prove whether our claims or hypotheses are right or wrong. So let's look at the data table, okay? She collected her data and she recorded them right there. So we're going to use the formula for rate. So remember, this is section 2.4. Rate of sublimation is going to be equal to the change in mass. So the initial mass minus the final mass divided by the time. Okay? So that's how much the mass is going to change, and that's how long it took to change. So this is going to be help us calculate our rate. Okay, change in mass over time. So we're going to do our first one. So the rate should equal the initial mass for trial 1. Let's do trial 1 first. Is 95.45 minus 67.25 divided by 3. So these are all grams and this is minutes. Okay, so if you put in your calculator 95.45 minus 67.25 divided by 3, you're not going to get the right answer. Why? Because remember, when it's written like this as a fraction, you have to first do what's on top and then divide it by what's on bottom. Okay, so there's like parentheses here. Okay, even if you don't see them written, they're there. So you have to do that first and then divide by 3. So if you want to put it in your calculator, you would put parentheses 95.45 minus 67.25, parentheses close, divided by 3. That's what you would write in your type in your calculator. Okay? And if you do that, so actually do it, make sure you know how to do it, because on the test I can't help you do it. Make sure you do it and you get 9.40 grams per minute. Okay? So that's our first trial. You should be able to use the same exact method, plug in initial minus final divided by the time, and get the other 2. All right? So do those, and then you can check your answers with the answer key and make sure you got it right. Okay. So the next part that we're going to do is the graph. So it's nice and clear. It tells you what to put on your axes for the graph. So we've got our y-axis and we've got our x-axis. Okay, so what's our x-axis? Our x-axis, it tells us, is going to be time. And our units are going to go in the parentheses next to the variable minutes. Our y-axis is going to be the mass. Parentheses, units are grams. All right, so now we need to choose a scale for our axes. So how do we do that? Well, we're going to look and find what's the highest mass there. We've got initial and final, so we have to plot both of them. So which one is the highest? Hopefully you've recognized it's 95.45. So we need to go up to at least 95.45. So usually we do a little bit higher. So I'm going to pick 100. That's a nice round number, right? So I'm going to count, I'm going to look at my scale. It looks like my y-axis has a little over 10. So I think it's going to work a little over 10 boxes. So I think it's going to work if I go by tens, right? Every box is going to count as 10. So I tried that and it worked. So you should do it too. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay? So yours will look slightly different because you're doing it on the paper. I'm doing it on the whiteboard. But basically just go by tens and it should work. If it runs out, it's not enough, well then you have to make your scale, every box, count for more. If there's too much space, like you end up here and you haven't used up the whole scale or most of it, then you should make each box count for less, okay? So you can stretch it out more. But don't pick weird numbers like 3.5 or something like that. Try to pick whole numbers. It's a lot easier too if you go by like 2s or 5s or 10s or 1s, something like that. Okay, time, we look at our data table. What's the largest time? Well, the time is the same for all of them, right? There it is. Okay, it's 3 minutes. So we only want to go to 3 minutes. So I found that if I did every 10 squares as a minute, that gave me a nice spread out axes. Okay, you don't want to do every square as a minute. Otherwise, it's going to be all jammed right here, and it's not going to be a nice graph. We want to use up as much of it as possible. Okay, so now the way that you're going to graph this is you have two masses. So you have to ask, when is the initial mass taken? Initial mass was taken when the time was equal to 0 minutes, right? Right when you started the timer. So that's what you need to put for when you're graphing the initial mass. We're going to do it at 0 minutes. The final mass, when did you take the final mass? Right? What did it say on the timer? Well, it was when the time was equal to 3 minutes, right? So we're going to put our final mass right over here where the x is 3 minutes. Okay, so the first one should be 0 minutes was 95.45, so I'm going to put that there. The final mass was 67.25, so I'm going to go over to the 3 and put a dot there. Then I'm going to use my straight edge on my ruler. Remember, on this test, you must use a straight edge or a ruler. Okay, and you get a nice straight line like so. Okay, and this is going to be trial 1. So you can either do it as a key off on the side, or I'm okay with you just labeling it there. All right. If it was a professional graph, though, for like a lab that you're turning into your professor, you should always do a nice key with a legend in the corner. Choose a different color or style of line or something like that, so that it looks more professional. Okay, so the next one, trial 2. The initial mass was, do you see it? 63, right? 63.25. So I'm going to plot that right there. And the final mass was 52.25. So I'm going to plot that there. And I'm going to connect it with my straight edge. And draw my line. Beautiful. Super professional looking. Okay, and then the final one, trial 3. The initial mass was 14.5, so it's just going to go right there, right below what 15 might be, and 9.45 is the final mass, so right there. And then once again, I can use my ruler. And I line it up carefully, and I draw my line. All right, and so this was trial 2, and this was trial 3. You could put numbers too, that's even clearer. All right, so that's how we analyze our data. So notice, as the initial mass went down, the rate or the change in mass over time got smaller. So here we have a very steep slope. So that means the change was a lot more. Here it gets more flat, and here it's the flattest. So we see our rate going down. So in this case, our rate, and in a lot of graphs that have like mass or volume or things changing over time, the rate is equal to the slope. Okay, so that's another way that we can check our data quickly without having to do all those calculations. All right, so the last thing you need to do is the CEE paragraph, all right? So the CEE paragraph is asking you to state your claim. Your claim is your hypothesis, okay? Your hypothesis. So what was the claim? The claim was the larger the mass, the slower the rate. How do I know that? It's in the first sentence there at the start, okay? The larger the mass, the slower the rate. We look at our data. Was that the case? No, the largest mass was 95.45. The rate for that was 9.4. The smallest mass was 14.5. The rate for that was 1.68. So actually, the larger the mass, the higher the rate, okay? And that's also supported by our graph. Our first trial has the much steeper slope, whereas our last trial, the slope is almost completely flat. Okay, so you need to state the claim. Then you need to state your evidence, which is what I just stated, and then explain it like I did. So evidence are the numbers, the data points, okay? Evidence are these data points. Initial mass was this, rate was this. Initial mass was this, rate was this. You need to state that in your paragraph. Then your explanation. So I have this posted on, will be posted with the answer key, but I will read it to you as well so that you can have an idea. So what I said was, the claim was the smaller the piece of dry ice, the higher the rate of sublimation. You can also say it the other way. The higher the piece, the larger the piece of dry ice, the smaller the rate of sublimation. Either way, it's the same thing. My evidence. The data says when the initial mass was 94.45 grams, don't forget your units, the rate was 9.40 grams per minute. When the mass was smaller, 14.50 grams, the rate was smaller, 1.68 grams per minute. Okay, that's just facts, right? I'm not assuming anything, I'm just stating the facts as they are. Then my explanation. Therefore, the claim was wrong. Okay, the larger the initial mass, the faster the rate of sublimation. Okay, you could stop there, but you could also add some more by saying, I think this is because ... Right? So I said, I think this is because there's more dry ice available to sublime. Okay, maybe you want to talk about the surface area or you have another thing. That's like your